Okay, now I'm back with example 4 of simplifying radicals. This particular problem got a little bit more flavor to it because I have a negative 2p out here in front of this radical. So this time I'm doing the cube root of 648 p to the 5th q to the 2nd. So if you paid attention to the last example that I did the cube root of the number, then the cube root of this variable, and then the cube root of this variable. So the last one wasn't cube root, but I'm doing the cube root of each individual term inside this. And because this is a product, the product property allows me to be able to do that. So doing the cube root of 648 times the cube root of p to the 5th times the cube root of q squared. So again, don't forget that the variables are easy. Numbers are not bad either. You just got to know your perfect cubes. And there is a perfect cube in 648. And that perfect cube happens to be 216 times 3. So I'm going to have to separate this times the cube root of p to the 5th. And don't forget that we're dividing that exponent by 3, not 2, 3. And then this cube root of q. Let's take a look at this. The cube root of 2 in the instant happens to be 2 since negative p times 6 times the cube root of 3. And then right here, this is 3 goes into 5 one time with a remainder of 2, and any remainders stay inside the radical, so it has a remainder of 2. And then lastly, 3 does not go into 2 no times, so the q squared part stays inside the remainder. So if you pay attention to it, everything that's on the outside of the radical, we're going to multiply together. So if I multiply this is negative 2p times 6 times p. This is negative 2p squared times that 6 times the cube root of, and everything that's not on the outside of the radical stays inside the radical. And this is going to be negative 2p squared times 6, which is going to give me negative 12p squared times the cube root of 3p squared q squared. And I'm sorry, I kind of got this bunched up, and I promise not to do that again. It's not a good habit. Mathematically, you want to space the problem out. So if you pay attention to it, we did the cube root of the number and then the cube root of each individual variable. And we simplified each one of those, and everything that came out, we multiplied together. And then everything that's up on the radical stayed up on the radical as a product. Okay? All right, so when we talk about adding and subtracting radicals, excuse me, there's 2 must-haves. It must have the same index and it must have the same radicand. So you cannot add or subtract 2 radicals. So think about adding and subtracting radicals as combining like terms. So when we talk about like terms, if you had something like 3x squared plus 4x, notice that you can't add those because it doesn't have the same exponent. Same concept. If you had the square root of 3x plus the cube root of 4x, we cannot add those 2 things together because they have different indexes. Or let's have a situation where they have the exact same index, but different radicands. You can't combine these two. So again, this has different indexes, definitely different radicands. This has the same index in radicands, or the same index, different index and the same radicand. So these are three examples of where situations where you can't combine these. There's nothing that we can actually do with that, so we kind of leave it alone. This right here, we can pull out an x because it's a square root, but other than that, there's nothing we can do to simplify that. So we pretty much leave that is the same way that you would leave that. So if we take an example, and this is example 5. So the key components is this. Okay, some key components. The first thing I want you to pay attention to is this. So just like in the previous problems, I have -5 times the square root of 32 plus 7 times the square root of 18. Notice here that I definitely have different radicands the way it's written. However, if we treat this problem as this one problem as two separate problems, where just like in the first 4 examples where we were simplifying radicals, let's simplify this and see what we get. So this is -5 times the square root of, and there's a perfect square in 32. Then we have 16. So 16 is a perfect square, and I don't want to have to keep breaking this up as a square root of 16 times the square root of 2. So I can actually take the square root of 16, which happens to be 4. And then I can't take the square root of 2. So that stays inside the radical. Okay. Make my 2 a little bit better. And then we multiply this. This gives me -20 square root of 2. Now let's go back up here. And I'm just going to carry this addition sign down. And now what I'm going to do is just simplify this radical. So what I have is 7 times the square root of 9 times 2. Now, 9 times 2 is going to give me 18, but 9 is a perfect square. So what I have is 7 times 3, the square root of 2. So we multiply the 3 and the 7, and we get 21, the square root of 2. Now, think about the must-haves that we have to have in this problem. In order for us to combine these, it's got to have the same index and the same radicand. They both have the same index and they both have the same radicand. So what I can do is I can add these coefficients, and we put this together. This is -20 plus 21. That's 1 the square root of 2. We don't write 1s on the outside of the radicals, so it's just square root of 2. All right, so in example 6, we kind of step it up a little bit. We actually have a radicand that has a variable in it, and then we have a coefficient on the outside of this radical that has a variable. So what we have to do is do the exact same thing, and we just focus on each one of these pieces, one piece at a time, and simplify it, and then the parts together. And typically, when you do it, it may or may not come out with the same radicand and the same index. It just depends. So first of all, we're going to focus on this part of it. And there's a perfect square in 72. That perfect square happens to be 36. So if I take 4, the square root of 36 times 2x to the 5th. And then here, to simplify the variable, I take and divide by the index, because don't forget that what the concept of this right here means. What's the relationship between the index and the variable exponent? So the index is always the denominator for the variable exponent. Okay, so now what I have is 4 times the square root of 36 happens to be 6. And then I'm going to go ahead and pull out the variable at the same time. 4 goes into 5 one time. with a remainder. So it has a remainder of 1. So what's left is going to be 2 and the remainder of 1 from that. So now what I have is 4 times 6x times the square root of 2x. And if we clean this up, this gives us 24x, the square root of 2x. All right, so I'm going to go back up here. And we're going to focus on cleaning this up. So as I take a look at that, I'm sorry. Oh, Lord, I messed up. I put an index of 4. It should be 2. Oh, man, I messed it up. And then 2 goes into 5 2 times with a remainder of 1. Okay. All right. Just made one mistake. Because I had to back and look at my problem because I'm transferring the problem from this to this. All right. So now 242. The square root of 242 is perfectness is 121 times 2, and then this is x raised to the third, and we divide this exponent by 2. So what I have is 3x times 11, and the 2 goes into 3 one time with a remainder of 1. So what's left up under the radical is the 2 and then a remainder of x with an exponent of 1. So use my properties of exponents and multiply the coefficients. I get negative 33x squared times 2 to the square root of x. And then if we combine the 24 minus 33, I think that is going to be negative 9x squared times square root of 2x. And I need to get my negative in there. And this is this problem simplified.